For decades, Pluto lived at the edge of the known solar system, a small, lonely world most people thought of as nothing more than a frozen outpost. It was distant, dim, and wrapped in cold that seemed to hold fast. When NASA's New Horizons sped past in 2015, the first close-up pictures stunned everyone. People expected a dull, simple ball of ice and rock. Instead, New Horizons showed an astonishing world. Smooth plains of frozen nitrogen, towering mountains of water ice, and a thin, delicate atmosphere that reached much higher than anyone guessed. Those images changed how people imagined Pluto, but they also left a puzzle that refused to be solved. The puzzle began with temperature. Scientists used models that seemed solid and well-tested. Based on what they knew about nitrogen and methane in thin atmospheres, they expected Pluto's upper air to sit at around -73 degrees Celsius. The data from New Horizons didn't match. The real measurements were far colder, by more than 30 degrees. That kind of mismatch wasn't a small glitch. It meant the simple energy math of sunlight in and heat out didn't balance. Something was bleeding heat from Pluto's atmosphere in a way the models didn't account for. For years, researchers checked instruments, reran calculations, and tried to find missing pieces in the usual places. They adjusted assumptions about sunlight, particle sizes, and chemical mixes, but the numbers stubbornly refused to line up. The atmospheric cooling was real and strong. It hinted at a process the community hadn't considered carefully enough. Then, in 2017, one scientist proposed an idea that at first sounded strange to many. What if the little particles that made Pluto's haze were doing more than drifting passively through the air? What if they were actively changing the planet's energy balance? This scientist, Shi Zhang from the University of California, Santa Cruz, suggested that the tiny solid particles in Pluto's high atmosphere, the complex hydrocarbons often called tholins, could absorb high-energy ultraviolet light and re-emit it not as visible light, but as mid-infrared radiation. That part wasn't wild. Many materials emit heat in infrared. What was surprising was that this emission could act not to warm, but to cool. Zhang argued that the particles might radiate energy away extremely efficiently, letting Pluto shed heat into space from high in the sky. In effect, the haze could act like a large thermal shield, stealing heat from the atmosphere and sending it out as infrared. It was a different way of thinking about climate control on a planet, one that pushed solid particles into the lead role instead of gases. Most of the field greeted the idea with skepticism. Planetary climate was usually modeled with gases controlling temperature, carbon dioxide on Venus, methane on Titan, and so on. The notion that suspended solids could dominate temperature control seemed to go against those well-tested frameworks. Still, Yang's model made a clear, testable prediction. If the haze truly radiated in the mid-infrared, then it should produce a distinct glow at those wavelengths, so faint that only the most sensitive instrument could see it. That instrument was the James Webb Space Telescope's mid-infrared instrument, known as MIRI. Years passed. Then, in May of 2023, an international observing program led by an astronomer named Tanguy Bertrand turned Webb's attention to Pluto and its largest moon, Charon. Webb's power lies in its sensitivity and spectral range. Using several mid-infrared bands, 15, 18, 21, and 25 microns, the team scanned the pair carefully. For the first time, the telescope could separate the faint heat signatures coming from Pluto itself and those coming from Charon. The results surprised even the researchers who hoped to see Zhang's effect. Pluto's infrared emission was stronger than what its surface alone could account for. When the team subtracted Charon's contribution and isolated Pluto's atmospheric signal, the spectrum matched the prediction, a glow in the mid-infrared consistent with solid particles radiating heat. The haze wasn't just scattering sunlight or serving as an inert dust layer, it was actively emitting infrared light. The signature fit what Zhang had proposed. In plain terms, the haze was glowing in wavelengths that let Pluto dump more energy into space than models had allowed, and that explained why the atmosphere appeared far colder than expected. If this were just a detail about a single small world, it would still be interesting. But Webb's observations suggested something bigger. The same mid-infrared fingerprints were visible on other hazy, cold worlds. Titan, Saturn's largest moon, already famous for its thick orange atmospheric haze, showed similar mid-infrared features when Webb looked along its limb. The signal there was even stronger than on Pluto, hinting that solid particle radiative cooling might be a common process wherever the chemistry and conditions let tholin-like particles form. Triton, Neptune's moon, once thought to be mostly inactive, showed faint hints of comparable activity as well. A pattern began to emerge. Hazes containing complex hydrocarbons could act as powerful regulators of atmospheric energy across the solar system. Under Webb's precise spectroscopy, those haze particles revealed chemistry far more complex than scientists had imagined. The tholins were not simple soot-like compounds. They showed dozens of hydrocarbon chains and included molecules with nitrogen and oxygen bound into their structures, elements that, on Earth, are central to biology. Some researchers noted that similar photochemical reactions in Earth's early atmosphere have long been suggested as contributors to prebiotic chemistry, the kind that might kickstart life. The implication was provocative. These hazes were not only influencing temperature, but also driving complex chemistry on a planetary scale. There was an even stranger hint in the data. When scientists examined how the haze emitted and reformed over time, they found a rhythmic pattern tied to Pluto's own day. The mid-infrared emissions seemed to wax and wane in a cycle that matched Pluto's roughly 6.4-day rotation. That suggested the haze reacted in an organized way to the arrival and retreat of sunlight. In other words, the particles absorbed energy, changed chemically, and then emitted it in a cycle that followed the planet's daily rhythm. It blurred the line between simple physical reaction and a system that behaved with something like timing and regularity. As Webb's observations piled up, the implications widened. Astronomers began to look outward to exoplanets, worlds orbiting other stars, and saw echoes of the same spectral features in atmospheres around cool red dwarf stars. A few distant planets, with names like K218b and TOY 700d in the files, showed faint mid-infrared dips that resembled Pluto's haze lines. At first glance, this was confusing. Those worlds were larger and warmer than Pluto, yet they exhibited similar spectral behavior. If hazes could regulate energy so effectively, they might create stable surface or near-surface conditions on planets otherwise considered unlikely to host mild climates. That changed how scientists thought about habitability. Perhaps a planet didn't need Earth-like oceans or thick sunlit atmospheres to maintain temperate conditions. Maybe a chemistry-driven haze could stabilize temperatures and protect fragile surface environments from extremes. But as the excitement grew, so did the mystery. Some of the Webb data hinted at something else, something that didn't fit into standard atmospheric physics. A number of internal reports circulating within NASA and other research centers flagged non-thermal infrared emissions that didn't follow radiative equilibrium models. That language is technical, but simply put, the observations suggested Pluto was losing heat in ways models couldn't explain, and the analysis hinted at sources of energy that weren't accounted for by sunlight alone. One line in an internal summary stood out and set off intense curiosity. It mentioned that haze particles exhibited properties consistent with conductive microstructures, tiny formations that might carry electrical current. If true, that would shift the picture dramatically. Instead of a passive chemical fog, Pluto's upper atmosphere could be behaving in electrically active ways, conducting and redistributing energy in complex patterns. The image of Pluto as a simple, inert ball of ice started to crumble. Then Webb did something unexpected. When the telescope was pointed at Pluto's night side, what should have been the deepest cold and darkness, it detected faint, rhythmic, mid-infrared pulses. At first, observers assumed these flashes were reflections from Charon or stray light artifacts. But the geometry and timing did not fit simple reflection. The pulses were too regular, too precise. They repeated every 247 seconds. That period matched, with unnerving precision, another signal Webb had recorded elsewhere in deep space months earlier. The coincidence was odd enough that many scientists asked hard questions about instrumental effects and data processing errors. Spectral decompositions were run. The team split the signal into its components and looked for familiar shapes. What they found surprised them. The pulse amplitude variations, when plotted, formed a set of ratios that matched some of the most famous mathematical constants: the golden ratio, pi, and Euler's number. The math read like a message, a sequence of numbers long associated with geometry, circles, growth, and fundamental mathematics. If the result held up, it wasn't random noise. It looked structured, and structure can be read as information. Not everyone accepted that interpretation. In professional science, extraordinary claims demand extraordinary evidence, and there were immediate calls for independent verification. Official hands reached for conservative explanations: resonant particle scattering, instrumental interference, thermal artifacts. Those possibilities had to be ruled out, and the reports reflected caution. Yet the more the raw data were reprocessed by different teams and different software, the more the periodic pattern refused to vanish. Some researchers reported faint electromagnetic echoes that seemed to come from beneath Pluto's icy shell. Spectrometers picked up reflections that suggested a highly reflective layer roughly 12 kilometers below the surface. The reflections did not match the signatures of ordinary rock or water ice. They looked metallic in character. Again, this was a preliminary interpretation, subject to many checks. But if a reflective, layered material existed beneath Pluto's outer shell, it raised questions the field had not been prepared to answer. Rumors and whispers spread beyond formal channels. The idea that Pluto might harbor a buried structure, vast, spherical, and reflective, captured imaginations. Some descriptions in leaked notes suggested a body spanning a significant fraction of Pluto's diameter. Others were more cautious, calling for better data and more modeling. Within the halls of some research groups, heated debates unfolded. How could a small world that formed in the cold outskirts of the solar system now show signs of internal layering with unexpected reflective properties? Could geological processes alone produce such a result? Or was there something more to consider? As the debate intensified, the political side of science reared its head. A number of internal documents related to these observations were pulled from public access. One report, labeled with terms like atmospheric anomalies and Pluto-Triton comparative study, was classified for internal review. Official statements from NASA emphasized caution and the need for further study, citing possible technical explanations. But behind closed doors, some staff were reportedly asked to sign non-disclosure agreements concerning certain datasets. A few scientists, uncomfortable with that approach, chose to resign. The departures fueled leaks and speculation. The leak that captured the public's attention was a passage from a scientist's private notes. "Pluto is not what we thought. It's something built." Those were dramatic words, and without context, they were explosive. For the scientific community, they were a prompt to slow down and apply rigor. For parts of the public, they ignited conspiracy-fueled stories about hidden structures and alien artifacts. The difference between careful analysis and sensational interpretation was suddenly a fault line. Independent researchers who managed to obtain raw Webb data did their own processing. Some reanalyses confirmed the mid-infrared haze signature and its cooling effect. Others found the rhythmic pulses too, though interpretations varied. A subset of analysts suggested the 247-second oscillation could be a natural resonance, an acoustic or electromagnetic mode in Pluto's interior or atmosphere. Another group pointed out that mathematical constants can appear in many contexts without being intentionally encoded. Patterns sometimes emerge from complex systems without an originating mind. Both views had technical merit, and both needed more data to be settled. Yet the public narrative raced ahead. Media creators and online channels picked up the most striking elements. Mysterious mid-infrared glows, rhythmic pulses, metallic reflections beneath the ice, and internal memos pulled from public circulation. The story's emotional power was obvious. It read like a classic scientific thriller, an underdog world, a surprising discovery, a maverick theory vindicated, and a possible cover-up. People wanted answers, and they wanted them now. Scientists, for their part, returned to the instruments. Webb's MIRI continued to observe Pluto when possible. Other observatories were asked to look too, though not all can see Pluto the way Webb does in the mid-infrared. Ground-based telescopes, radio arrays, and other space missions contributed complementary data. Examination continued, and the careful, often slow work of science marched on. A few lines in the leaked documents raised deeper questions. One passage suggested that the haze's conductive properties could allow it to function like a planetary circuit, transmitting energy in filaments across wide regions. If haze particles could organize into conductive networks, they might explain how energy moved from place to place in ways not previously considered. Those filaments could, under certain conditions, concentrate energy and then release it in pulses. That description sounded almost mechanical, but it could also be a natural outcome of complex coupling between charged particles, magnetic fields, and photochemistry. The line between built and self-organized suddenly mattered a great deal. Another odd detail in the leaks was the observation of faint electromagnetic activity above Pluto's terminator, the region between day and night. That activity seemed to pulse with a regular rhythm. Researchers entertained options: aurora-like processes driven by solar-wind interactions, electrical discharges in a charged upper atmosphere, or resonant coupling between atmospheric layers and subsurface structures. Each hypothesis carried testable predictions, but none matched every observed detail perfectly. The most provocative claim, that the rhythmic pulses encoded mathematical ratios, drew attention beyond astronomy. Mathematicians, philosophers, and engineers weighed in. Some argued the occurrence of constants, like the golden ratio, pi, and e together in one signal was unlikely to be coincidental. Others cautioned that human pattern seeking can impose meaning where the natural world offers stochastic variation. The debate itself highlighted a broader truth. Data require careful interpretation, and extraordinary implications require extraordinary proof. As the controversy unfolded, a quieter revolution continued in the science itself. The realization that solid particles could substantially control atmospheric temperatures forced modelers to rewrite climate codes for small, cold worlds. Laboratory experiments designed to mimic Pluto's upper atmosphere sprang up in university basements and national labs. Researchers burned methane under ultraviolet lamps, cooled the gases to low pressures, and watched what kinds of complex hydrocarbons formed. They probed optical and infrared properties, electrical conductivity, and how layers of these particles settled and changed over time. The new data fed back into planetary models and helped explain why some worlds looked unexpectedly cold. Webb's findings also pushed planetary scientists to rethink habitability. If hazes can stabilize conditions and shield surfaces from damaging radiation, then distant, hazy planets orbiting faint stars might have more benign environments under their cloaks than previously believed. That broadened the search for life in the galaxy and sent exoplanet teams scrambling to add mid-infrared haze indicators to their lists of promising signs. Ideas that had once seemed speculative, life originating in the dark, slow chemistry of hazes rather than in sunlit oceans, began to gain scientific legs, if slowly and cautiously. Back on Pluto, the drama continued. Webb's occasional night-side detections kept analysts awake. Some datasets showed the pulses fading, others showed them flaring. Earth-based timing and cross-checks did not always line up cleanly, a reminder that observations across light years face many technical hurdles. The calls for more targeted observations grew louder. At the same time, the scientific community's handling of internal reports and data access prompted questions about openness in research. The resignations and NDAs became part of a broader conversation on how institutions communicate uncertainty and the responsible release of preliminary findings. Through it all, the public remained fascinated. The images of Pluto, the pale heart-shaped plain, the jagged ice mountains, the layered bluish haze, helped keep interest alive. The story's emotional core was simple. A familiar underdog world, once thought dead and small, revealed secrets that forced scientists to rethink much of what they took for granted. Whether those secrets pointed to new natural physics, surprising chemistry, or something more enigmatic, they demanded attention. Some scientists returned to restraint and skepticism, pointing out how scientific history is full of premature declarations and alluring but incorrect narratives. Others embraced the chance to explore wild possibilities, knowing that the truth, whatever it would likely be more complex and more interesting than the simplest headline. Between those poles, the discipline moved forward. Data collected, models revised, experiments performed. The tale also highlighted the unpredictable power of great instruments. Telescopes like Webb don't just confirm expectations, they reveal the unexpected. New windows on the universe create new questions, and those questions reshape the work of decades. For Pluto, Webb did what New Horizons could not. It read the planet's faint thermal whispers and exposed how tiny particles, chemistry, and perhaps electrical processes interact at the edge of sunlight. The results do not fit neatly into old categories, and that discomfort is where real science lives. At the end of the day, no single narrative can claim absolute truth. Some parts of the leaked story, haze-driven mid-infrared cooling, chemical complexity, links to Titan and Triton, rest on solid observational ground and on reproducible analysis. Other parts, the buried metallic sphere, encoded mathematical signals, and conspiratorial cover-ups, remain contested, debated, and in many cases unproven. The best path forward is a patient, methodical one. Collect more data, test more hypotheses, and be honest about what is known and what is speculation. The drama around Pluto matters not only because of its potential shock value, but because it illustrates how science actually works when the universe surprises us. Observers find anomalies, theorists offer explanations, instruments test them, and the community argues, replicates, and refines. Sometimes the answer is a new kind of chemistry or an overlooked physical process. Sometimes the answer is human error that gets corrected. And occasionally, the answer is something that forces a fundamental rethink of how we see the world. For anyone watching this story unfold, the lesson is simple and profound. The cosmos is vaster and stranger than our neat categories allow. Instruments like New Horizons and Webb do more than collect data. They expand the set of questions we can ask. Pluto, once an icon of the forgotten, became a test case for how chemistry, particles, and perhaps even electrical processes shape a planet's face. Whether that leads to evidence of widespread prebiotic chemistry across the outer solar system, new ideas about planetary circuits, or simply a better understanding of haze physics, the journey of discovery is already changing the field. And while the leaks and rumors will always attract attention, the real excitement lies in the slow, careful work that will separate fact from fiction. Researchers will keep observing, labs will keep experimenting, and models will keep improving. In time, the fog of speculation will lift and be replaced by a clearer picture, one that may be just as surprising, but also more reliable. Until then, Pluto remains a symbol of the unknown. It teaches humility, that even in an age of powerful telescopes and global science networks, a small distant world can still surprise us and force a rewrite of long-held ideas. The James Webb Space Telescope has opened a new chapter in the study of icy worlds, and with every new observation, humanity inches closer to understanding the strange, beautiful physics playing out at the edge of sunlight. Whether those findings turn out to be the result of chemistry, physics, or something even more mysterious, the search itself is the point. An unending curiosity that drives scientists to look, to test, and to learn. If the listener wants more, the next Webb observations, follow-up experiments, and the community's own debates will be where new answers are found. The universe, as always, waits to be read. And in places like Pluto, it has stories to tell that are stranger than fiction and more fascinating for the careful work that will eventually reveal their truth.